How to implement or how to utilize the three-phase programmable voltage source in MATLAB Simulink. So first let's get the voltage source, and for that we'll go to this library. In library we'll go to SimCaps. In SimCaps we'll go to power system, and in power system we'll go to specialized technology. In specialized technology we'll go to fundamental blocks, and in fundamental blocks we'll go to electrical sources, and in electrical sources here we have three-phase programmable voltage source. Let's add this. So here we have three-phase programmable voltage source. Now we'll take one load resistance, so let's add three-phase RLC branch. So here we have three-phase series RLC branch. Double click it. We'll take only resistance and we'll make it 100 ohm. That's it. Okay, so we have connected this source to the resistance. Here we have a scope. Now we'll take a voltage measurement. So here we have a voltage measurement block. Basically we want to measure the phase voltage of these three lines. So what we'll do, we'll connect the positive to this line and the negative to neutral, and that's how we'll be able to measure the phase voltage. We'll do the same thing for another line. So here we have created the entire circuit. In this circuit, this is our supply side, this is the load side, this is our neutral. Using these three voltage measurement units we are going to measure the voltage, and using this scope we are going to observe the waveform. Now it's time to understand three-phase programmable voltage source. What is inside this source? So first thing we will be able to get is positive sequence. In here we are supposed to add the amplitude, which is basically the RMS voltage, which is phase to phase. Then we are supposed to add the phase or the degree by which your first phase will delay, and the third one is frequency. So let's say we are keeping the amplitude 100 as it is. We are going to change the frequency, which is 50. Let's make it OK, and now let's run. But before running I would like to tell you that we have still missing one block. We're supposed to add one block in this simulation, and then we're supposed to run. But first let's see what happens if without that specific block if we run the simulation. Now let's run. So when without that specific block if we run the simulation, it will create an error. And what is that block? That block is this power GUI block. Let's close it. Let's add that power GUI block. Here it is, power GUI block. Now we have that power GUI block, and now let's run the simulation, and it's completely fine, right? So power GUI block is needed when we do the simulation. But what is the need of this power GUI block? And if you want to understand the exit requirement of this power GUI block, I have created a separate video for that. The link is in description and above here in card, so you can refer that video a little later. Right now let's open this thing and observe the waveform. We'll make it horizontal zoom. Here you can see we have given the amplitude VRMS phase to phase, which is 100 degree, but over here you can see that the peak is 80, so the RMS is much less than that. But let me tell you that this quantity is phase to phase, or we can call it as a line voltage, right? So the line voltage is 100 volt, and what we are measuring over here, we are measuring the phase voltage, and that is why that is little less than the line voltage, and that is less by root 3 times. So that is why the voltage you are getting over here, that is little less. And if you want to observe the line voltage, let me show it to you. Here I have connected this as a line voltage. Now let's run. So now here this is the line voltage. So the amplitude that we have applied is 100 volt RMS. So you can see that the peak is almost around 145. So the RMS could be 100 volts. Now here the phase delay we have provided is 0. What does this mean, 0 phase delay? That will be clearly understood through the waveform of phase voltage. So let's close it. Let's open it, the waveform of phase voltage. In phase voltage, the A phase is starting with this 0 and that 0 is represented over here. Now instead of this 0, let's say if I'll make it 120. So what we are doing, we are providing delay of 120 degree to this phase, and in order to understand that, just observe the sequence. The first one is yellow, then blue, and then red. Now let's close it, close this too, run this thing and open it. So previously we have seen the sequence that is yellow, blue and red, but now you can see the sequence has changed, that is first blue, then red and then yellow. That means it has shifted by 120 degree, right? So close it. So I think this section is clear to you all. This is the amplitude, phase delay and frequency. Let's make the phase delay 0 again. So the next is time variations of, and here we have three possible options. First we'll go for the amplitude. So when we select amplitude, this open again a new selections and new parameters. This one is type of variation, what type of variation we want. So in that we have 4 type of variation. Let's say first we'll go for the table of time amplitude pairs. In this variation, what it will does, it will create a variation in amplitude with respect to time. So here the amplitude values, and that is basically a per unit value, and each value of amplitude corresponding to each value of this time, right? So here you can see per unit 1 at 0 time instant, then per unit will become 0.8 at 0.1 time instant, and then at 0.15 time instant the per unit value will become 1.2, and then again at 0.2 time instant it will become 1.0, right? So let's make it okay and run. So here you can compare at 0.1 time instant the amplitude has reduced to 0.8, and at 0.12 time instant the amplitude has increased to 1.2 per unit, and again at 0.2 it reaches up to 1.0, right? But now this variation is for all the three phases. If you want this variation for particular one phase, then what you're supposed to do, from here you're supposed to select variation on phase A only, and then okay, close it and run again, open it, make it horizontal zoom. So here you can see up to 0.1 all the phases are same, but after 0.1 phase A is reduced to 0.8, and then phase A is shifted to 1.2, and at 0.2 time instant it is again unity. So by selecting this option you will be able to make changes in only one phase, right? Now let's again open this block. Now we'll go for the second option, and that one is step. Here what you're supposed to add, you're supposed to add the step magnitude. Here we are providing step magnitude of 0.5. Starting time and ending time, let's say starting time is 0.5 and ending time is 0.8, right? So at 0.5 the step will start, and at 0.8 the step will again come back to its normal position. Let's make it okay, run. So here you can see, so at 0.5 time instant the output is increased by 0.5, or it will add 0.5 into the rated voltage. But now what if you want to reduce magnitude by 0.5, then over here you're supposed to write minus 0.5. Say okay, run again and open. So when you have provided minus 0.5, the magnitude will reduce by 0.5 from 0.5 to 0.8 time instant, or whatever time instant you have provided. Close it again. So here what happens when you select a step variation that you have seen, and I think that is clear to you. The next is ramp. The rate of ramp is provided 10, right? And start and end time will keep the same, 0.5 and 0.8, right? It is the starting and ending time. Let's close it, run again, and here you can see at 0.5 to 0.8 the ramp of 10 increases the voltage with the predefined slope, and that slope is 10, and then after it will be constant with the previous magnitude. Now close it again Let's open it. Now I'll go for the third one, and that is modulation. In modulation, it will multiply a modulated signal with the current supply. Let's say the amplitude that we supposed to modulate, that is 0.5, and modulation frequency, let's say we are keeping it 20, right? And we want to modulate, we want to integrate this change in between 0.5 and 0.8. Let's say okay, run again. Now let's see the waveform. So here you can see from 0.5 and 0.8, a signal of 20 Hertz frequency and a magnitude of 0.5 is multiplied with this. So this type of variations is created in between these time. Let's say you are changing this frequency to 2 Hertz, right? Let's make it okay, run it again and open it. Here you can see the signal of 2 Hertz frequency is added with the magnitude of 0.5 with this original signal, and that's how this type of swell you can see from 0.5 to 0.8 time instant. So close it. So here we have seen these varieties of variations that we can create into this voltage source. Now at last we have one more thing, fundamental and harmonic generation or harmonic generation, right? So when you click it, you have few more options, and over here what you're supposed to add, you're supposed to add the order of the harmonics, the amplitude of the harmonics, and phase degree of that harmonics, and you're supposed to say whether that harmonics is 0 sequence, 1 that is positive sequence, and 2 that is negative sequence. So these are the things you're supposed to add. So let's say we have added these parameters, say okay, run it again and observe the waveform, right? So this is the variation that occurs because of adding of those harmonics. Let's open it. Now close it. Now here we have seen the variations that is possible with the amplitude, but using this programmable voltage source, it is not the only amplitude, but you can make changes with phase and frequency, right? So in these two parameters also you can change the output of this programmable voltage source the way you want. Now I want you to implement these two changes, phase and frequency, and observe what is the change in its output.